Hi, I'm Dylan, and I've been programming with databases for about 20 years. I'm in several discords for programmers, and it seems like there's a lack of clear introductory content on how to choose a database and various other related topics. So here it is. So the first thing I'd like to say, and that I'd like you to remember through this whole thing, is that none of this is magic. Physics and logic apply to it. So you shouldn't be intimidated because it can be learned. You can make big mistakes with databases, but you can also accomplish bigger things than you could without them. Um, a database is a big system, generally, that is coded so that you can use it like a much smaller system. So, what we're going to do is talk about the purpose of a database, when to use that database or a database, the difference between SQL, NoSQL, and NewSQL, um, a little bit of database implementation, tips and tricks for when you're starting out. And then I'll conclude and sort of go back over everything in very short detail. So we can start by asking the question, what are computers used for? Because a database is a program on a computer, and this sort of helps you understand why you would use it and what it really, like what the purpose is of using a database rather than a chunk of code you write yourself. So, database computers generally are used for communication, data storage, and calculation. Those are the three primary functions they have. Um, and databases need to do some of all of these, but they're really heavily focused on storage. So they a database is essentially a very large computer program or a very specialized, some of them are written to be as small as possible, designed to store data as efficiently as possible while at the same time allowing you to do um, calculations upon that data and communication of that data as necessary with other servers or clients or so on and so forth. So, when you think about databases as an application, they are useful because they're doing something which is actually very difficult. The amount of data that a computer holds is much more than it can process all at once. So you have layers and layers and layers of places to store data that get progressively bigger as they get slower to access. So you start with the processor at the center. And then outside the central processing portion of the processor, there are caches that hold data. And then as you go further out, is the main memory, and the main memory is still fairly fast because it's still, it's still not physically, it doesn't require physical motion, but it's significantly slower to use main memory than it is to use the caches that are on the die. And then as you go further out and you have a hard drive, which a hard drive is much faster now than it used to be because you have solid state drives, but like the orders of magnitude involved in going from memory to your hard drive and getting data off of your hard drive is almost as big as the orders of magnitude in astronomy. So you have to go to Alpha Centauri time wise and bring data back when you have a ton of data to get. So when you talk about working with a database system that is managing all of this file loading or all of this data loading and unloading for you, it's doing a lot of work that you do not want to have to do because all of that work becomes operating system specific, processor specific. It becomes very, very hardware specific eventually. And that is not something that, as a programmer, I mean, I might be qualified to do it, but I would need a ton of time and I just don't want to spend it. So that's the biggest thing you're going to get out of operating with a database system. Well, this leads into the question of what else databases are for. And in the case of calculation, um, you can do depending on the type of database management system you're using, you can do queries and aggregation and query-based data changes. But generally, what you really get out of using a database for calculation is that um, because the data is better organized and you have that organization, you can perform operations on large data sets much more quickly and much more efficiently than you could in code generally. So on the storage side, you get some significant benefits. Um, you get all the ACID principles when you work with a relational database, with an ACID compliant database, which are atomicity, consistency, isolation, and durability. So these things are very, very important and useful when you're dealing with data. So atomicity means that if you change data or you work with it, you can break that information apart. And consistency means the data doesn't break the database. You can set things up so that the data will always be valid. And then you have isolation, which is when you break your transactions into individual particles, they operate individually and they will lock appropriately so that you can always get the data in a valid state, and it always reflects exactly what at the time of execution, you get exactly what you are expecting, and it is true. And then that system will also be durable in an ACID system. So if the whole system goes down, it doesn't mean your database is inoperable. When you boot it back up, it will work again. And that comes also with an abstraction when it comes to an architectural layer. So you don't have this code, all the code managing these complicated things mixed in with your other code. And you have a centralized server for it in many cases, or you have a centralized interaction system for it. And let's see what else is on this slide. Other stuff. Yes. And division, it divides the labor into logical parts for sure. Yeah. So that you can put your database onto a server or into a cluster of its own that you do not need to share with your non-data management things. You can boot up or it doesn't even need to be a cluster. It can just be a Docker container. That this database can be a system that does not need to interact with your other systems except through very well-defined interfaces. So just in general, the point of tools you don't write is solving problems you don't want to solve. And in general, databases solve a bunch of problems that are difficult enough and high investment enough that solving them has made people billionaires. So you don't want to try and solve that kind of thing on your own without the 30 years of background and experience that people who write database engines have, and that these engines have undergone in testing. There are, of course, ways for this to fail where you aren't really trying to solve a problem big enough, or your data is way too disorganized, or you choose the wrong system for you choose the wrong type of database for your data. But in general, you don't want to try and store 5 gigabytes of data in an array or it's a homemade data structure. It's just a bad idea. These are the 3 primary classes of database management system out there right now: Relational Database Management System, or RDBMS, NoSQL, and NewSQL. So I've included this list of various engines because it's entirely possible you've used one or another of them, and that will give you some sort of frame of reference. So these are all systems that can handle large amounts of data, different scales of data with different purposes and different sort of properties. Like we'll cover what the differences are very shortly. But here's just a point of reference. Relational databases systems used to be what people thought about when people talked about a database. The primary example that everybody used to have on their desktop was Access. But that has changed over time, and it's really easy to get free ones. So you can get SQLite or Postgres or MySQL all for free. And so relational database systems are in many ways the gold standard for what a database can do, but they come with some costs. So in a relational database system, the data is structured in that the data has um, a schema that defines how it is built and how what exactly is in it, and it's very strongly typed generally. Um, and you know exactly how you need to put things in to make it work. The schema is more difficult to work with because you have to know what it's going to be like ahead of time, and that slows down development. The server itself um, is almost always a single server. You can cluster database servers in RDBMSs, but it makes things much harder. Generally, database system an RDBMS is designed to scale vertically, which means you get um, the benefits of a stronger computer show up. So you put 16 processors on a computer and tons and tons and tons of memory, and that's your database server, which is different from the NoSQL systems. Um, Generally, though, like the relational database systems have kind of converged so that they all have most of the same features. They have different bells and whistles for integration, but the the core ACID compliance and SQL language features and extra features which are different per language. So every it's so Oracle has a SQL version, and Microsoft has a SQL version, and MySQL has a SQL version, and all of them are ANSI compliant in that they do the base SQL stuff, but then they also have an extended instruction set that they can do more advanced things and integrations and so on and so forth. But all of them have in large part much of the same functionality. Now that is not completely true. Obviously, Oracle has more functionality than Postgres in a lot of areas, and Microsoft has much better integration in some ways with desktop and so on. So yeah, and then we're gonna look right here real quick um, at a database diagram that I've put together. So I put together this is what a diagram for a little database that I looked at building could look like, and you've got um, join tables, you've got IDs, things are linked, things are relational. And this is vastly different from what a NoSQL database normally looks like, because a NoSQL database is almost never strongly typed. Not never, but it is uh, not. I mean, MongoDB can type your variables, but you can also break that typing in certain situations. You can tell it to let you. Um, but MongoDB will not let you do this kind of linking. And if you do this kind of linking, the index is between things. And anyway, um, core of this story. This is what a relational database diagram could look like. This is a tiny one. They get huge. So, having covered relational databases, now we're going to move on to NoSQL, which is the second most common database, and it's also they're generally quite mature. NoSQL databases are generally specific uses. So if you have have a a system that you're looking at that needs a specific kind of functionality, you're going to have several options for NoSQL databases, and there will be one that makes more sense because of the way that the data is structured and the functionality that that database has. Because they're special use, NoSQL databases are generally much faster to set up, but on the flip side, they don't follow all the ACID rules. as traditional relational database engines. They follow some of them, and there are levels of consistency available, but they don't do everything out of the box as reliably in some situations, most situations, because it's a trade. They've all made a trade. There are several kinds of NoSQL databases. The two I know best are object stores and key value stores. So I'll give a little talk about each one. Object stores are designed to hold objects of a certain shape, and they can be indexed on those object properties. In the case of MongoDB, I'm not sure about all of the object store databases out there, but you certainly can in Mongo. So for example, you have this warehouse full of barrels. Now these barrels could be different sizes. They aren't in this like example thing. The cars are a better example because the cars can be SUVs, they can be, they can be Miatas, they can be, they can be big cars, tiny cars, they can be all sorts of different kinds of cars, and they can have all sorts of different properties, some of which are required, some of which aren't. Who knows? And they all can be stuffed into a parking spot, and then you can pull them out, and you can do some inventory of them as they come into the parking lot. And they can be massively different shapes and sizes. You could have you could put a semi truck in this. You could put it in this parking lot, but you could put it in a MongoDB. And it's much quicker and easier to set up because you don't need to know all of the properties ahead of time that each car will have. So in a relational database, if you want to know what kinds of tires and group by the kinds of tires, you need every single car to have a tire, or you don't need, but it's much better. And in but more than that, if you want to be able to group by tires easily and sort of normalize and make sure you only have so many, you can clean your data easier in a relational database. But more than that, like, you couldn't just say, well, there's a tire field in this table now, because the data has it. That doesn't work in a relational database, but it will in an object, in an object store. So with an object store, you have a key value store, which is even less constrictive on what you can put into it. You basically send the key value store a key and the data that goes with that key, and it stores it for you. This is very useful for things like caching. So if you have a website and you want to store all of the website's data, or all of a calculated page that you're going to need to serve many, many times, then you can calculate it once and store it in the object store, or in the key value store. Sorry. Or you could do, like, if you were building a multiplayer game and you wanted to send the same game state out to 50 people, you could have you could have all the inputs done, chunk it through on a hardcore processing machine, put that on a database to be served to everybody, and you would serve everybody the same thing. That would be very useful to make sure that you were serving the same thing to all 50 people, for example. So I have included NewSQL for completeness, but it doesn't really belong in an intro course. It's designed to be able to scale the way that NoSQL does, but still maintain ACID properties. So it is designed around the concept that you can have many, many servers and then have them retain the atomicity and the consistency and the integrity, like I forgot the durability and the other I thing. It's designed to hold all of those things. It's complicated to do. You need to be running Kubernetes and so on. So I suggest that you do a lot more research than I can give you right now before you try this. So to close on the technical portion of this, these are a few notes on implementation. Number one, you're going to want to use an object relational mapping layer, or an ORM. This is Entity Framework. Django has one built in. I think Spring is the Java one. I'm not sure. No, that's not. Anyway, you want to be using a way to define your database structure in code, regardless of the database interface that you're using, except if it's a key value store like Redis, where it's, you're essentially working with a big dictionary. This is because if you're defining your database structure and the queries you're using in code, it's much easier to keep track of exactly what you're doing. And um, and it avoids several issues that come with databases. So you may have heard of query injection. An ORM avoids query injection because it sort of sanitizes all your inputs naturally. It does a lot of not the heavy lifting, but the syntax stuff that you want to be completely aware of on its own. And you can think of it as a programmer and work with it like a programmer works with an object rather than learning a whole separate language. And that actually turns out to be extremely useful. Um, second, the primary choice between SQL and NoSQL, or RDBMS and NoSQL, is a design ahead of time versus toss in choice. When you design ahead of time, you get some significant benefits in that you have a good handle on what your data looks like and what you're doing with it. But that will slow down your development cycle at the beginning. It can speed it up later. It can mean that your data, your process will be easier to work with later. And there's definitely, if you're building an application for reporting, pulling data out of and aggregating data that's coming out of a SQL database is more performant than with a NoSQL database. Especially if you're doing proper indexing, which is the next thing I want to talk about, which is indexing is important. Okay, so the way that databases know, if we go way back to the solar system metaphor, all right, the way that databases know how to what to pull off of Alpha Centauri and into the solar system and then into the sun to do some processing on is generally by an index, which can be held, which is smaller than the data itself, but tells the processor what things are needed for any specific query. So those indexes are much more effective in a RDBMS, and they're also super necessary. So if you're having performance problems with the database, one of the first things to do is look at whether or not your indexes are defined and set up properly. And that's one of the things that comes with having an ORM, because in some ORMs, you can actually set your indexes as part of the, code. And if you aren't doing that, then you can have some significant problems with versioning and with, booting up new instances of databases and so on and so forth. So you want to be sure that your indexes are set up properly. And the last thing is that relational databases can enforce referential integrity much better. Now, referential integrity is something I haven't talked about much at all. But if you want every single object of a specific type to have certain properties and certain data inside of it, then you need to be enforcing your referential integrity. Yeah. And then there's a bunch of other little hints here. You want to try and keep all your indexes and primary data in main memory if possible, which is easier to do with a smaller machine on a relational database, because relational databases, due to normalization, don't have as much duplication in the data. When you start talking about environments, it's pretty easy to set up a tiny local server in any engine. And generally, you're going to want to maintain an API between your database server and the outside world, because your database server generally will contain stuff that you just don't want the outside world to have. And also, subscribing to my channel and liking this video means that I might make more like it. So if you do like this video, you should do both of those things. Now, later, I don't care. Now is smarter, because you might forget. That'd be just terrible, wouldn't it? So one question I was directly asked was whether I would prefer cloud or local servers or my own hosted servers. Um, I do not like waking up at 4 in the morning to deal with a server problem. So I like cloud servers. That's the, most important thing you should learn from this whole talk. So to wrap up, we've covered what the purpose of a database is. Basically, to save you from solving a bunch of very difficult problems, including file access at scale, um, concurrency issues, race conditions, all sorts of file level locking things that you just do not want to deal with, and sort of time sensitive issues. There's lots of things that a database will do that if you want to do them in code at scale, you want to do them for a very specific purpose. And if you can find a system that will solve this problem for you, it's a problem you don't need to solve yourself. Now we've covered SQL and NoSQL very in depth. Or not in, I mean, okay, let's not, this is not an in-depth. I didn't say that. This is not in-depth. This is a basic. All right. And so the things that we can say basically about SQL here are that SQL is organized. It has ACID consistency. It has more upfront time investment than NoSQL because you need to design your schema, but and it has reliable results that don't scale infinitely. You can scale a NoSQL database pretty much infinitely because you can just throw more servers at it. The problem with that, though, is that when you start throwing more servers at it, getting data out of it is not as easy. So if you're scaling, if the thing you need to scale for is reporting, you won't actually get the scaling you want from scaling a NoSQL database. However, there are some other advantages that NoSQL has in that they are very purpose specific, and being purpose specific allows them to do exactly what you want faster in many cases. They are in some ways not as general purpose, although Mongo is an extremely good general purpose database for many applications. In fact, Mongo is in some ways a better general purpose database than a SQL database because of the quicker implementation. But they have, because they have this rapid design, because they're not as stringent about what they do, there are some limitations in the end. Yeah, so that's what we've covered. Right. And so that's the end of this. I suggest if you have further questions, you want me to make more videos, you join my Discord, which is in the thing down there. If you just want to watch the videos, you can subscribe. I'll probably put some more up. And if you like it, then, it's more likely the algorithm will put this up and more people will see it. And then it's more likely I can make the time to make more of these. Anyway, thank you very much for your time and attention. Right? Yeah. Okay.